Welcome back to another exciting session of ECE 441's demonstrations for the laboratory. This is lab number 3, and today what we are going to be working from is really all available on the website, and you can go to the ECE course website, click on handouts, scroll down to demo number 3. After this particular video has been encoded, you'll have it available and you can then view that. But for today, what we will be working through is indicated in this PDF file of demo number 3, and that will allow you then hopefully to work through these 3 different handouts that are provided on the website. And in the process of this lab, we will actually be implementing quite a few MATLAB commands or scripts, and those are also available for download, and you can then put those in the appropriate working directory of MATLAB and execute those M scripts to help you do your controller designs required in lab number 3. For example, the first handout is a pre-lab exercise, and what you will want to do is continue with the system that you've had all along and fill this out in terms of number of masses, spring number, and total mass. Write down your system, and then you will be able to, in step B, actually start executing the MATLAB script PLEAD to help you do your controller design. So now that I'm back on the browser window, what I'm going to do is go ahead and open up the demo number 3 handout and essentially work through that for today's demonstration. This particular lab number 3, is concerned with designing a controller, G sub C of S, that now is not going in and measuring position and velocity for full state feedback. It's actually simply measuring the position variable, and it has to filter that in some way to duplicate or try to recover that velocity information that it now can no longer measure explicitly. And that's what I'm trying to say here, that in lab number 2 we could measure both position and velocity and use those in a feedback setting. Now in lab number 3, all we can do is measure position, and we have to figure out how best to filter that in order to make this system behave the way that we want it to behave, or really change the behavior of our mass spring damper system, which you have identified in lab 1 and actually verified again in lab 2. In lab number 3, we're working with 2 different kinds of controllers, one being a phase lead controller and the other being a PID controller, or a proportional integral derivative controller, which is indicated by these 3 terms. Our system, open loop, is given by the following pole zero diagram. We simply have 2 poles, and the root locus for this particular system, if we just had a gain, would go up and down at 90 degrees, and the closed loop behavior would simply be indicated by or determined by the amount of gain that we've introduced in the system, and that might then just make our system a little more oscillatory, but it's not going to change the damping at all. And so our overshoot is actually going to be deteriorated if we increase the gain K in that system. Let's now talk about the phase lead controller design. In this particular case, we have 1 0, 1 pole, and a gain, 3 parameters, and we're going to try to use that to reduce our settling time. The settling time in the open loop case is maybe 4 seconds. Now we want to reduce that so that the settling time is actually occurring in 1/2 of a second. Using our design specification concept for a pure 2-pole system, we know that 4 time constants represents a 2% settling time, and that's given as 4 over sigma, which we want to be less than 1/2. Solving that for sigma allows us to see that indeed we want a sigma value, or the real part of our closed loop poles, to exceed 8 in magnitude. or in terms of S-plane location, we want this vertical line as our constraint line to be sketched at -8, and we want our closed loop poles to be to the left of that vertical line at S equal -8. What we want to do then is, remembering what we had these two poles which could be at -2, -2.5, -1.5, it depends on your system. We actually want to move those over into the left half plane by what? By having a 0 somewhere here, and we actually want those poles to be pulled over such that that distance is 8, and we then allow, if we're to the left of that particular location, we will satisfy our settling time specification. What possibilities do we have in terms of, if we do introduce this phase lead controller, there's a couple of possibilities for the phase lead compensation or the root locus diagram that results. And it all depends on the relative location of our poles and zeros. We could actually attract these poles down to the real axis, and we would have then a re-entry point. One would go to the right, one would go to the left, and then break away after colliding with this pole that's coming to the right, and then go off. We probably won't see that in our particular system because our poles are significantly far away from the real line, and they may bend over and then go up, but they may not get all the way down. And so if I could duplicate that design symmetrically down below, that's what I would try to be doing. But you can see then that we might have to settle for our closed loop poles being there and possibly here. We have a lot of activity going on today, and so that particular phone call will live in infamy. But we have the following possibilities for our root locus pattern, and no matter what we do, we are going to always have, let's say, these two complex roots and a third pole on the real axis between where we've located this 0 of our phase lead controller and this pole of our phase lead controller. We're going to have those 3 poles, and what we want to do is make sure that this particular pole and those 2 poles are to the left of this vertical line, which is a distance, let's say 8, away from the origin. And that's what I'm trying to say here. We want that 0 to the left of S equal -8, and a way to try to determine where we might put our pole is determined by the Centroid formula that we've derived from our rules of magnitude condition and phase condition. The Centroid formula says that we take the sum of the poles' real parts and subtract from that the sum of the zeros' real parts and divide by the pole 0 excess. We know sigma 1 and sigma 1, that's actually the real part of our complex roots of the open loop system. Z is our controller's 0 and P is the controller's pole. What we're trying to do is determine those at some value so that our centroid, or the asymptotes, are far enough into the left half plane to allow our closed loop poles to live left of S equal -8. Let's suppose that we have a system, and your system may be different in your case, but let's say that I have spring number 3 and 1 mass. It has poles roughly in the open loop at -2.5 plus and minus J 17.5. In that situation, our sigma sub 1, or the real part of those open loop poles, are at 2.5. Plugging that in, we then see that we still have these unknowns Z and P, Suppose we locate our 0 to the left of -8, and specifically suppose we let the 0 be at -10. We now only have one unknown here other than the centroid, and suppose we want our centroid to actually be at -15, or the asymptote line will originate at -15. That's where our root locus branches are being attracted to, and hopefully they'll be attracted to -15 rather quickly before they get too large an imaginary part. If we now replace sigma sub a with -15 and z with 10, we can solve for p, and in this particular case we end up with a pole location of 35 to give us a centroid located at -15. We now have our phase lead pole and 0 locations determined. We now need to find a gain k to give us the appropriate closed loop pole locations. Suppose we pick our pole that's living between what? The 0 at -10 and the pole at -35. We know we have a closed loop pole between those locations. Suppose we push it all the way from -35 all the way down to -17.5, not quite at -10. If we evaluate the gain formula at -17.5, and assuming that our system has a K hardware of 4,000, and again this was for spring 3, closed loop or open loop poles at -2.5 plus and minus J 17.5, we end up with a K value of roughly 0.3. That says then that we have now determined everything that we need, all the parameters in our phase lead controller, and we can use that information to try to determine where are the actual closed loop poles. We picked this value of 0.3 to give us one pole at 17.5. Let's see if the resulting imaginary poles, the complex poles, are acceptable. If we now solve this numerator expression, we end up with this formula, and that gives us a cubic in S. We can find the roots, and the roots are then at -17.7, almost 17.5. This was approximately 0.3, and our complex roots are -11 plus and minus J34. That zeta is actually then going, or the angle associated with those poles is 72 degrees, which gives us a zeta value of 0.31. That's not a very good zeta, meaning we're going to have a fairly good overshoot, but the overshoot is actually going to be even worse than what a pure two-pole system would be, because we have this 0 now that we put into the controller at S equal -10. That percent overshoot then, because of the small zeta and this 0, is going to be worse than what just the zeta of 0.3 would give us. You can refer to figure 513a to get some insight into the severity of that degradation, but this is only again going to be an approximation, because we also have a third closed loop pole at -17.5, and that is actually going to help our percent overshoot. So this 0 worsens our overshoot, this helps. The net combination says that we will still probably be a little worse than what we would see percent overshoot wise from a pure two-pole system. The other thing that we might be wanting to understand is the steady state error that results from a phase lead controller. Here is just a diagram of what we are looking at in the lab. We command our system to move to 2,000 counts, that's our reference input, and our controlled system with the phase lead controller may produce an output response that looks like the following, where I've now stretched out time. This is supposed to be happening based on our design to occur in less than a half a second. But our steady state error, if we just had a unit step, again we'll have to scale that up to 2,000 subsequently, but just for a unit step we would multiply this transfer function that relates our reference input R to the error location E, and here is our unit step given by 1 over S. With the final value theorem we can obtain for a unit step again a steady state error given by the limit as S goes to 0 of 1 over 1 plus G sub C of S, G of S. If we evaluate those transfer functions at 0, we end up with a steady state error of 0.48 when we put in a unit step of 1. That means that we're 0.52 units away from 1 when we put in a unit step. That means we're not even halfway to where we wanted to go. That means then that if we're a little bit more than halfway because our error is 0.48. In our particular case, if we commanded the system to go to 2,000 counts, we can now use this expression, scale that 0.48, which was due to the unit step, by 2,000. We put in 2,000. What is the final position, x steady state? And we see that we're actually only getting about halfway towards our desired position, final position, by getting to x steady state of 1,000 counts instead of getting to 2,000 counts. So we will then use MATLAB to try to determine how best to do the phase lead controller. And I may just try to do that right now if I can find what I need. What you will want to do is click on phaselead.m on our website, handouts page, download that and put that into your particular directory, working directory of MATLAB. If you now have done that, I'm going to see if I can find MATLAB here. And you will then start MATLAB, switch to the appropriate working directory, and hopefully I will be able to find the location that I need to find, and I will then demonstrate how you can use the code that's on the website to do the phase lead command or the phase lead design, and you do not have to necessarily do it all by hand. Now hopefully I am in the right location. You can do a PWD to see if you're in the right directory, or you might have it actually on one of your windows. I'm actually going to increase this. I don't need to see all of the left panes so much. And let me now say that I want to execute plead. So I need to go within the lab, and now that's my working directory, and now execute the mscript file plead. The first question that it asks for the input is to give the numerator, and our system doesn't have any zeros, which means we just have a constant numerator. I'm assuming my numerator is what? 4,000. That's going to be your K hardware divided by your total mass. In my case, the total mass is 1 kilogram, and I'm assuming my hardware gain is roughly 4,000. The next question it asks for is to enter the denominator polynomial, and you'll know what that is for your system. Mine is roughly s squared plus 5s plus 312, which corresponds to 2 poles at minus 2.5 plus and minus j 17.5. I enter those numerator and denominator polynomials for the open loop system. That's now in, let's say, stored in MATLAB. The next question it asks me for is to enter a zero location for the phase lead controller. That I'm going to select to be 10, which is what we said it should be in our design process. And now our pole, what did it tell me I needed to have? I've already forgotten what that was. Let me say that that is now at 35. And MATLAB is now, should be drawing a figure. And this is now the resulting root locus pattern. The code is designed to first show you this particular figure, and then you have to enter press the Enter key, and it will then allow you to find a location on that figure window with your mouse. I'm going to hit Enter again, and now I'm trying to locate what? The closed loop poles that I want. Our design said we wanted to be at about 17.5 for our gain for the real pole coming in from -35. I'm going to then put my cursor there and see where the resulting closed loop poles are. And the closed loop poles are now roughly at -11 plus and minus j, probably whatever it was that we calculated in the earlier diagram, or in the earlier part of our discussion. Let's just pick a phase lead controller of 0.3. It won't quite put us down at -17.3. And we now have calculated not only the resulting step response, but also the plants transfer function, the phase lead controller transfer function, and we've also calculated the closed loop poles. We've calculated the settling time. Again, this is all within P lead of 0.39. That meets our specification. Our peak value is not even getting to 2,000 counts. It peaks, though, rather quickly at 0.08 seconds or 80 milliseconds. The percent overshoot is pretty bad. It's 86, and our final position is then 1,050 in terms of counts. And that seems to be pretty consistent with what we did with paper and pencil in the PDF file of the document that we did for demo number 3. And that's how you can actually go and examine your particular system with using the MATLAB commands that are now available to you via PLEAD. All you have to know is your open loop plant, your zero and pole location, and then determine the gain that you need in order to give you the appropriate controlled with a phase lead controller closed loop system. Let's now return to the demo notes, and we're now ready to look at the second controller type, which is the PID controller type. The reason we're doing that is if we go back to MATLAB, we wanted to actually be, reaching 2,000 counts, and we're only going maybe a little bit above 1,000 in this particular system. That may not be acceptable. We may want to drive this actually to 2,000 and have zero steady state error. We're not going to do that with a phase lead controller or a phase lead controller by itself. We're going to introduce an integral term via the PID controller to help us eliminate those steady state errors due to constant inputs. Our design specifications now have changed a little bit. We want a settling time less than half a second. That's consistent. But now we want our closed loop poles. We just want a zeta value of 0.7. In a pure two-pole system, that corresponds to about a 10% overshoot. But here, I'm just wanting you to locate those such that the angle of the complex poles are less than 45 degrees. Because of the presence of the zeros in our PID controller, we will actually have much more overshoot than what would be available to us from a pure two-pole system. Now, the PID controller is an ideal controller. It's contributing 2 zeros and 1 pole. The 1 pole is fixed, it's at the origin, and our 2 zeros are what we have the ability to adjust or select, and then we can adjust the gain of that overall controller. Here are some possible patterns for a system controlled with a PID controller. We could actually locate those PID controller zeros to be complex and far enough into the left half plane so that these complex open loop poles are pulled towards those zeros. This pole at the origin that's due to the integrator would then just march off to negative infinity, and we might locate our dominant poles or select the gain value so that we get our poles there. And what we want to do is have those to the left of 8 and also within this wedge of 45 degrees. And we are wanting then those dominant poles to be somewhere out in that particular region. That's one possible location for our zeros of the PID controller. Another choice would be to have two real zeros that are not at the same location. This might be at -15, this might be at -30. Those are just numbers, but that would then what? Cause this pole at the origin, due to the integrator term, to go towards that zero. These two complex roots would re-enter the real axis. One would go to the zero wherever you've located it. The other one would move off to -infinity. And what we're wanting to do is ideally make this one be to the left of our vertical line, which might be what? Determined by our settling time spec, which is 0.8. And we would like for these complex poles to be living inside this 45-degree wedge. That's another possibility. A third possibility would actually maybe be the easiest to design with, and that is to locate both of our PID zeros at the same location. And we are actually, in this particular demonstration, we're going to locate those both at -20. One of the poles, which is due to the integrator term, is going to go to one of those zeros. These two are going to approach the real axis and re-enter. One's going to go to one of those zeros and the other one's going to go to the left. What we want to do then is locate our our closed loop poles, which are made up of these two complex and this real. We want to be to the left of this vertical line that's 8 units away from the origin, and the other specification was to live inside this 45-degree angle. Now, what's going to deteriorate our performance based on those two complex roots is the fact that we still have two zeros in or on the real axis, which are actually probably going to have a real part less than these two complex poles real part, and that will enhance or exaggerate the overshoot that we're going to see in that system. What we now want to do is determine what? By picking those two zeros at -20, we've now already fixed the numerator zero structure of our PID controller. All that's left to design is the gain value K sub D. And let's go ahead and fix that, or select the gain, such that if you remember this picture, what we're saying is we want to find the gain that puts this particular real pole at -13, and the idea is that that will be a large enough gain so that these that are moving from their -2.5 to plus and minus J17.5 are actually getting inside this 45-degree wedge. We want to know then what is the K that gets us to those triangle locations, and hopefully the gain to get us to 13 will put us here. If that puts us way down here and puts us maybe here and here, that may be a little too aggressive. Or if it actually puts us to where they re-enter and one comes here and one comes here, that's really probably too large for a gain, and we may want to back off of the gain to get us to that location, but we still want to try to get that triangle on the real axis to the left of this location that's 8 away from the origin. That's our goal, is to figure out what is K at that location, or to get us to 13. Again, we'll do that based on the magnitude criterion, or the magnitude condition. This is our positive complex pole. This is its twin that's in the bottom half of the complex plane. Here's the pole due to the integral term in our PID controller. Here are the two zeros that are contributed by the PID controller. this is the gain of our system, and we evaluate that at minus 13, that ends up giving us a derivative gain, or the gain on our controller, of 0.028. That's now determined our PID controller, and if we multiply this out, we actually see that we have a derivative gain of 0.028, a proportional gain of 1.12, and an integral gain of 11.2. With that particular structure, we can now determine from our characteristic equation the closed loop roots to see if those are acceptable. The numerator expression from this formula gives us this cubic. We find the roots. One's at minus 13, which shouldn't be surprising, and the other is at minus 52 plus and minus j 27.1. That obviously has a real part that's bigger than the imaginary part, meaning these roots have an angle that is less than 45 degrees. That may be a little aggressive, but it's not too bad. You may, if this is minus 70 and this is plus and minus j2 or j10, you may want to back off on the gain. But you now know how to back off on that gain to get what you want. And to do that, what you want to make sure is that this real part value is actually a little bit larger than the imaginary part, and that will satisfy the second constraint, which was to have an angle on those complex poles of 45 degrees. Let's now go into MATLAB and execute the commands. Again, you can do this based on downloading this PID controller and executing it in your working directory. It will ask you the same questions, your numerator of the system, which in our case is 4,000, the denominator polynomial, which is s squared plus 5s plus 312. It wants the PID 0 polynomial, which we said was s plus 20 squared. That's s squared plus 40s plus 400 if you multiply it out. And now it should have given us a root locus associated with that PID controlled system. This is what we're anticipating. This guy's going to that 0. One of these is going to that 0, and the other one is going off to infinity. We now need to hit the enter key and select a particular choice of gain. We wanted that to be at minus 13. I'll speculate that that's about a third of the way to 20, but from 10. And that says then that we need a gain of 0.03 to get us out to minus 13. Let me go ahead and just enter 0.03 for a gain. Again, that will then provide the following transient behavior. We obviously have settled by 1/2 of a second. We now have no error. We're locking on at 2,000, and our overshoot isn't too bad. It's a little bit large, and we can look at what the PID expression has now told us. Our settling time is 0.17. The peak has gone up to 2264. It occurs at 0.03 seconds. Our percent overshoot is 13%. We do not have a steady state error since our final value is 2,000, and that's what the integral part of this PID controller was all about. And that's what you have to do then on the lab, is figure out what your controller structure needs to be. You will then use that to help you fill out this particular handout, which is the pre-lab exercise. You'll fill in your gains for your PID controller, the 0 location in the pole. You'll fill out the proportional, integral, and derivative term gains in your PID controller, and then be ready to come into the lab and execute the procedural steps. And following those procedural steps, you'll be able to go back into MATLAB and actually do the following commands. So now I'm assuming you've created your data from up in the lab, and you now need to load that particular information. Let me go ahead and see what Lab 3 data files I have. here are some lab 3. You have 3 parts to the lab possible, an A part, a B part, and a C part. This is for one mass and spring number 3 that I've calculated several different trajectories. Suppose we want to then load in the B part, which is the phase lead controller. We would then load in lab 3B, and let's just say that that was the 3rd time I executed it. It's now been reformatted to allow it to be read into MATLAB. I'll rename that to be consistent with the program PLT3 that's going to work with the variable name data. I can now execute plot 3 for lab number 3's data, and it will immediately give me then the steady state value of 768, a percent overshoot of 108, a steady state error of 1232, and a peak time of 1600. And if I examine that, this is then what I get for a phase lead controlled system from the data. And that you will then report in the appropriate location here with the file conversion, or part 3, where it tells you how to convert and analyze the data. You will record this set of numbers for both the phase lead controlled system and the phase or the PID controlled system. Let me go ahead and just load that in and demonstrate that indeed I just have that, let's say the 2nd time, M1S3. And this response now has a 22% overshoot, and we do not have a steady state error, contrary to what we had in the phase lead, and our peak time is 0.08 seconds. Our damped frequency is 37 radians per second, and our settling time is 0.3 seconds. And that's what you're asked to do then, is use this information with PLT3 to actually fill out the final document, which is the file conversion and analysis portion based on your hardware measured numbers in the lab. We're now in the lab, and what I want to do is just walk through the steps that are necessary, which should be similar to what you've already done in labs 1 and 2. We're now in lab 3. You'll need to find the ECP icon or through the Start menu. First thing you want to do is get rid of the encoder 1 position counts. It's now at some random location depending on where it actually stopped. Let's then zero the position. We'll zero out those counts. The next task is to actually load the appropriate file or configuration file, and that will actually be on the C drive in ECE 441 and ECE 441 _lab3.config. That should configure it in the mode that we need it to be configured in. We then go to the setup the setup window, control algorithm. It should have the dynamic forward path button highlighted. We'll go, and it should be in continuous time. We'll go to setup algorithm. For our particular system, let's go ahead and implement the phase lead controller. Now it's written in a little bit different form. It's now in terms of polynomial structure. The S0 is actually the variable or coefficient that's a product of the gain of the phase lead and the 0 location, which in our case was what? 0.2 times 10, I believe, to give us 2, and then our, I can't remember if that's actually what it was for our phase lead controlled system or not. What was our gain? It was actually 0.3. So if we have a gain of 0.3, then we would have 3 times, or 0.3 times 10, or a gain of 3. This would be then 0.3, and our denominator polynomial, which are the R coefficients. R0, I believe, was 35 for our phase lead pole location, and R1 is a monic polynomial. We can then say that that's okay. The next thing, the important thing, is to click on Implement Algorithm. That now sends that algorithm to the hardware box, which should be turned on at this point. We can now go to the command and look at the trajectory, make sure it's the step. It's a little different. We're holding it on for a little bit longer time of 4 seconds or 4,000 milliseconds. The step count is still the same, and it should be in the closed loop step button condition. That's fine. Let's now execute that and run it. And you can see where we're settling now. We're settling at 1,000 counts, which is consistent with what we had said in the pre-lab. Again, we're settling at 1,000 counts, and we're commanding it to go up to 2,000. And we now want to wait until we have uploaded that particular data. And we will then do plotting, setup plot, plot data, and that should then be consistent with what we had for our phase lead controlled system. You will then want to export that raw data via the data window and save that probably to your Z drive and some directory within your Z drive. I'm not going to do that here, and I will now continue with what? Going back, and if you want to, you can actually abort the control. Right now it's closed. You could abort it and open it up. You could zero the position again if you want. And now what you want to do is set up the PID controller, change the button. We've gone to setup control algorithm, setup algorithm, and now our PID controller, we had a gain for our derivative of, I believe, 0.028. So we can put that in here, of derivative gain of 0.028. Our position gain, which we should have recorded, should be 0.28 times 40, which obviously I haven't done those numbers right now, but I could do that. So let me now just put in some numbers that I have worked with in the past. Let me just say that that's 0.022 for the derivative gain. Make sure you put these in the appropriate locations. The proportional gain, I'm going to say, is 0.88, and the integral gain is 8.8. Make sure you put the P, the I, and the D in the appropriate locations. Implement the algorithm. It's now closed. You can now execute that command. And you can see now that the integrator is zeroing out the error, and we now go to 2,000 counts with a control effort of 1.8 volts roughly. We now have properly executed the PID controller. We will wait for those samples to upload. We will quickly show then how to plot that via the plotting, setup plot, plot data, and we see that this looks consistent with the MATLAB program, PID. We can export that raw data, again, probably to the Z drive somewhere, and you're then ready to change those data files and then get those in the working directory of MATLAB and execute PLT3 to analyze that hardware data that you've now collected. That should finish up then lab number 3.